Hello everybody, Greg is here. I apologize for making another video about radicals. This topic is just so close to my heart I can't stop myself, but I promise that several next videos will not be about radicals unless something revolutionary happens. This is the AI generated pictures. This is two radicals in love, and this is about something with more details. And I did a video about frustrated radical pairs some time ago. This is a sort of update to the previous one. This is the work that actually pushed me to make this video. It's from the same group, by the way, who was involved with the silicon pyramid, but here they deal not with silicon but with aluminum, and by making this molecule and reducing the iodine atom with potassium graphite, they get a reaction with benzene of two such molecules. So this compound is isolated in 17% yield, and this is the mechanism that the scientists proposed. They see it also by some spectroscopical method. They see this radical, it's divalent aluminum compound with an unpaired electron, and the existence of such compounds was not yet proved, and this is one of the first proofs of such molecule. After this radical is generated, it reacts with benzene, you have another intermediate, and then this intermediate reacts with the second radical, and this product is formed. While of course this mechanism is possible, but I think that there is at least a good chance that it's not a stepwise reaction. First of all, the reaction is happening in benzene, so there's very few molecules of this radical and a lot of benzene molecules. Not only that, there is a TMS group, this trimethylsilyl, which can be a source of hydrogen, which can be abstracted by this or this radical, and the group does not report any hydrogen abstraction products. Because I'm so into this radical pair topic, I thought that there may be something like that. So there's two radicals of this type interact first, and in this condition they can be found in solution, and then they react with the benzene either stepwise or concerted mechanism. I hope that somebody will study this idea further later. I also started to look into literature to see is there any news with the radical pairs. And I'll start with this work, which is not very new, but still only 3 years ago. The group synthesizes those molecules. They get the radicals, those called Olympicenyl radicals. You can guess why. And they see that at higher temperature, you get separate molecules in solution, according to the spectroscopy. But when you cool the solution down, the two molecules interact by making pi-pi interactions. It's like graphene sheets interact between themselves. And when it happens, you get this equilibrium between singlet diradical and triplet diradical, while the singlet is slightly lower in energy. That's pretty interesting. That means that when the molecules are brought together by the pi-pi interactions, you have also the interaction between the two unpaired electrons, like in the biradical video I showed before, and some orbital forms in which those two electrons coexist. This paper does not discuss the orbital structure, they discuss some other electronic features, but there is a newer paper, it's actually a very fresh one, that do some study about such interactions. So what happens here? This group makes a cation radical and anion radical pair, and those molecules are held together firstly by electrostatic interactions. So the plus attracts the minus, or vice versa. There is two different pairs that they study. In this one, it's a complete triplet, so the electrons interact between themselves only through space. But in the second molecule, again, there is a pi-pi interaction happens, and here they see that the energy between the singlet and the triplet is very small. So here it's something like 50 kilocalories, and here it's only like several. And I find it very interesting. Again, from this picture, it's hard to tell why exactly this happens, but still a very interesting work. I was also wondering, can atom-centered radicals couple without electrostatic attraction or pi-pi stacking? How can it look like? And maybe the hint to such possibilities coming from the biradical chemistry when the two unpaired electron is in one molecule. There's still a lot of discussion in the literature about the so-called single pi bond. That's when the two unpaired electrons are very close to each other. Such molecule was synthesized in 2002 and published in Science. They called this molecule a deradicaloid. But those two publications in 2020, they actually prove and show that such interaction should be considered as a single pi bond. You can see from the shape of this orbital between those two atoms that it really resembles the pi bonding, and it also reacts as a pi bond. For example, it polarizes, so one side becomes plus and another one becomes minus, while two radicals, which when they're separated, they only neutral. But again, in this case, these two radicals are linked, are very close inside one molecule. It's really hard to imagine how you can separate it and still keep this interaction. But in the cube molecule, which I showed in the previous video, here, that's already looks like something that can be imagined as two separate molecules if you break some of those bonds. So here the distance between the silicon atoms 2.3, 2.5 angstrom. Here the distance between germaniums is more than 4 angstrom, like twice more. And still there is an interaction between those atoms in this molecule. This orbital here, according to the calculation, it corresponds to something like quarter bond, while here it is a real chemical bond. And this quarter bond is enough to keep the singlet structure very low in energy. Now allow me to take a step back and tell about our old work about interaction between two separate radicals, and then we go back to this idea. When you take this radical with 3-methyl-silyl groups on the silicon, it forms a dimer right away. However, if one of those methyls is substituted by the tertiary butyl, which is much bigger, you get several interesting things. First of all, those groups form a so-called umbrella conformation to protect the radical center. And those radicals very hard to bring together. And although we see a second order decay, we never get a dimer. According to calculations, the bond between those atoms here is very weak, like 8 kilocalories per mole or something. And that's why it doesn't survive. But what we never calculated is the other way. So if you turn them back to each other, can an orbital form here, like it formed in this cube? It probably will be more or less similar distance, maybe a little bit more, but maybe it's enough to form the singlet structure of the biradical. And maybe this structure explains the weird reactivity of this molecule, which we still do not understand. Thanks, I hope it was interesting. Like, share, subscribe, support Ukraine, and stay tuned for future videos.